In this video, we're going to be looking at the fundamentals you need to know before getting started with AWS VPC. This video isn't intended to be a deep dive on networking, but will hopefully cover the fundamentals you need to know to get started. We're going to be looking at a simplified version of the OSI model, IPv4 addressing, how routers are used in a network, how firewalls are used in a network, and how network address translation is used in IPv4. So here's a simplified version of the OSI model. At the bottom we have a physical layer, and this is a device-to-device transfer from the bits going from one device to another device by binary power on-off, like you would see in like a square wave. The next layer is layer 2, that has the data link. Now, each device on the network has a physical MAC address that's hard-coded into it when it's generated. Layer 2 allows those devices to communicate using the hardware address that is burned into it at manufacture. So that's where you might see MAC addresses. And switches use MAC addresses to route traffic from one device to another. So layer 3 is where IP addresses come in. It allows multiple isolated networks to be established and communicate to one another. The next layer, layer 4, is where protocols come into play. So that might be UDP or TCP or ICMP for like ping. And then we have layer 7, which is where your application sits. And this is typically mainly a layer used for data, but here we have, say, SMTP, HTTP, FTP or POP3. Here we have IP addressing, specifically IPv4. You may notice an IP address. That's quite a common home network IP address you may see. And each IP address is accompanied with a subnet mask. Now the subnet mask tells the host computer what part of the IP address is the network part and which part is the host part. And this is needed for basically communicating outside the network. For example, if we have another IP address, say 8.8.8.8, the computer is going to look at its IP address, its own IP address, is going to apply the subnet mask and work out, hey, 8.8.8.8 isn't in my network, I need to send it to a default gateway so it can go out to the internet. And we're going to look at that in more detail in a minute. So IP addressing allows us to have isolated networks, and each IP address is made out of 4 octets. So 4 octets, each octet has 8 bits, which can make up between 0 and 255, which is why IP addresses are limited to having 0 to 255. So in this example we have, say 1, which maps to 1, binary 1, and then we have 254, which maps to 254 in binary. If, say, this was to set to 1, that would be 255, for example, right? You don't really need to know the binary representation. If you want to go into more detail about how IP subnetting works, it's useful to understand it, and we're going to touch on it in the next slide. But for AWS VPC stuff, it's a bit low level. You just need to know kind of your CIDR notations, which we'll go into now. So here we are on IPv4 CIDR notation. So CIDR notation stands for classless interdomain routing. And it was introduced after the class ABC you may see in other material to make IP subnetting easier and allocate IPv4 addresses much more efficiently. Because as you may have heard, we've now run out. So CIDR notations basically map onto subnet masks. So a common one for home networks or even corporate networks might be a /24, and that has a subnet mask of 255.255.255.0, where the last 0 represents, okay, all of these bits are the host bit, and that will give us 256 IP addresses from .0 to .255. So that's 256 addresses. Now, not all of these are usable. For example, a .0 address is a network address and a .255 is a broadcast address. So other examples may be a /21, and that gets a bit more confusing. If you have a look over here, we have 3 more bits that can be assigned to the host. So that might be useful in some cases, but you can use subnet calculators to kind of work that out for you. And then another common one is a /16, where we have all of these 16 bits worth to assign our host. So that would give us 64,000 hosts in that network. You can see how the hosts are worked out. So we have we start with a 32-bit address, and we take off the CIDR prefix, which will give us 8 bits. Our 8 bits here would then 2 to the power of 8, as you do binary, would give you 256 addresses. Again, there's calculators online to help you do this, but just being aware that you have your CIDR prefixes. These are smaller, so you get less hosts, and then the lower number you have here, you get more hosts on a single network. If you were to go for a /8, that would just be a 255.0.0.0. So let's have a look at subnetting example. Now you might be like, what's a network versus a subnetwork? Now CIDR notation makes it really easy for you to break down a network allocation into multiple subnetworks. Okay, so we have our 192.168.0.0/16. Now our 16, if we have a look back to our other slide, gives us these 2 octets for hosts, this one and this one. But what we can do with subnetting is assign part of that host address to our subnet address, and that's exactly what we're doing here. So we can say that this is our /16, and then inside of our 16, we're not just going to put hosts in, we're going to put networks in there. And we're going to assign this octet to a network ID, so 0. And we're going to leave this octet for the host ID still. So this 24 is representing, this is the host ID that can change. And then if we have a look similarly over here, we have our network ID and our subnetwork ID. And then the hosts can still be allocated there. So we've also put here the subnet mask in case we need that, but that's equivalent to our /24. So here we have some hosts in our network. You can see each host is assigned the specific subnet ID that we've been talking about. So 1, 2, so X is 0, Y is 1, Z is 2. And all of these actually fall under this 192.168.0.0/16. So how does something in subnet X talk to subnet Z? So let's say my computer at 192.168.0.1 wants to set up a web server, or talk to a web server on 192.168.2.1. Well, this host is going to look and say, using this subnet mask, I can see that 2.1 is not in my network. And it's going to say, okay, I need to send it to my router. So it'll send it to a router, and then the router will forward it on to the relevant network. And we're going to have a look at that in a bit more detail right now. So before we get started on that, we're just going to have a look at Simplified Packet. So remember back to the beginning where we mentioned the OSI layers. This is kind of where it becomes important. A network packet has specific information at layer 2, layer 3, layer 4, and layer 7. So layer 2 is the MAC address, so that's the burned in hardware address on each device. Layer 3 is the IP addresses, so that's what we've assigned the devices, that 192.168. And then layer 4 is a protocol, so TCP, UDP, ICMP, and maybe what port it uses, like port 80 for HTTP, port 443 for HTTPS. And then layer 7, which is our kind of payload data. So here we can see a breakdown of the packet. This is really simplified. Like typically there's a lot more information in a packet, such as checksums, data lengths and stuff like that. So if you want more detail about that, go off and search about it. There's some links in the description below. But for the purposes of routing, this is kind of all the information that's required. So you have your layer 2, your MAC address, your layer 3, and your layer 4, which is saying the protocol and the port information. So routers. Routers forward packets to other routers or hosts that are connected to them. For example, think of your home network, where you have your router and your fiber internet and your end user devices, your home network basically. That's a router. It's going to take the information from one network, the WAN, your internet service provider, and it's going to receive a packet. It's going to change the source and destination MAC addresses, and it's going to send the packet out on the other network interface, your LAN. And that's why we have WAN and LAN. So let's have a look at how routers work. We've mentioned previously how the packet needs to leave network X and go onto network Z, but let's go into more detail to see what part of a packet do routers affect. Hopefully this will make the whole networking landscape click for you, because you'll understand the low-level details of how a router actually routes traffic. We have a PC on one subnet here, and we're going to give this a MAC address of A. It has an IP address of 192.168.1.2/24, and the router has an IP address of 192.168.1.1 and a MAC address of B. Now, I've mentioned earlier that routers have two network interfaces, or a minimum of two network interfaces. So on its other network interface, it's going to have an IP address of 192.168.6.1 and a MAC address of C. And then there's another PC sitting on this network over here that has 192.168.6.5 and a MAC address of D. So what's going to happen is this PC wants to send a packet to this PC. So the first thing to do is the computer is basically going to populate this packet. So let's say we're just sending a ping request, for example. It's going to say, okay, layer 2. So before we do layer 2, let's have a quick look at the IP address. So it's 192.168.1.2, okay? But our target is 6.5. And now let's have a look at the subnet mask. So the subnet mask is saying this shouldn't change, and this shouldn't change, because that is our network. But if we have a look over here, we can see that 6 kind of breaks that rule. It's not on our network. 192.168.6 is not our network, and thus we can't send the data to it directly, and we're going to have to send it via our router. Now what happens behind the scenes is that decision's made, and then something called an ARP request is also made, which says who has my default gateway. So that's broadcast to all the devices on the local network and say, hey, I kind of need to get out of this network. Who has 192.168.1.1 so I can send a packet to you, and you can route it for me. So that goes out to all the PCs on the network, and then the router will respond, I'm B, right? So that's how we know how to populate for layer 2, and that's called an ARP request. So we know we need to send it out of our network, so we've done our ARP request to work out here where do we need to send this data, and then this is responded, I'm B. So the source we're going to put in is A, because that's our source computer there, and our destination where we're going to send the packet is B, and then we want to send the packet to the device on our other network, which is 192.168.6.5, and we're going to put the source IP address in there of our network, or our computer, and this allows the destination computer to respond to us. So we're going to put that in there, 68.1.2, and then we're going to populate all the other layers that we might need, and we'll send that packet onto the network. So the packet's traveling on the network, and we're ignoring all the layer 1 stuff, so it's sending bits of data, and it's going to reach the reach a router. So it's reached a router, and the router is going to read this. It's going to say, okay, so you want to get your data to 192.168.6.5. Let's have a look for you to see where I need to kind of forward this information onto. So it has something called a route table that says all the data for 192.168.1 is on this interface, for example, and all the data for 192.168.6 is on this interface, right? So it's going to have a look at that route table, and this is something you need to know for AWS VPCs. It's going to have a look at the route table and then send the traffic out of a certain interface. So here it's made the decision, and it's going to say, okay, I need to send this data on 192.168.6.1, or that interface at least, so our MAC-C interface. So what it's going to do is it's going to edit the packet, and we want to leave a layer 3 source and destination intact, because that's kind of a point-to-point information. But what we're going to change, because we're changing networks, is the source address for the layer 2. So it's going to delete this for us, and it's going to say, okay, I'm sending it onto this network now. My MAC address is C. And then it's going to do a similar ARP request here thing. So it's going to say, hey, who has 192.168.6.5? And then this one's going to say, hey, I'm at D. Right, so it's going to come back to here. And then this is going to populate the packet and say, hey, okay, that needs to go to D, layer 2 switching, please work it out for me, and off I go. So now the packet comes in, and when it reaches the host, it's going to say, okay, I am D, yep, I'm allowed to read this packet basically, or I want to read this packet because there's tons of network traffic going on in this network. I only really want to pick up what I need to. And hey, great, I am also 192.168.6.5. So I'm now going to process this packet and send a response. And the response is pretty similar, just all in reverse. Something to note before I kind of change the topic is ARP requests are cached. So the ARP request might not happen every time, but when a host kind of talks to a new host on the network, it will ask it and then it will kind of cache a response. So that's just kind of a side note to just be aware of. So sending the data back is pretty much exactly the same, just in reverse. So our source becomes our 6.5, our destination will be our 1.2 over here. Our source MAC address will be D, our destination MAC address will be C. The layer 2 transfer happens here, where the router picks it up, changes the source MAC address to B and the destination MAC address to A, and then sends the packet on its way. So routers were basically just changing the packet at layer 2 level and forwarding it onto the network that it may be connected to. So if you think of your home router, that's going to forward any traffic upstream to a different router, and then that router might send all the traffic upstream again, and then you'll hit a router that is connected to lots of networks where it will all split out to your multiple ISP providers, and that's basically how networking works on the internet. There are bits like BGP, which you might want to learn if you're looking at AWS Direct Connect, that it basically broadcasts the different ways and routes available on the internet, which is kind of how internet routers work. So NAT, or Network Address Translation, was introduced for IPv4 to basically mask lots of IP addresses behind a single IP address. Now you'll see this with your home network, where you have your 192.168 network, but your public IP might be something totally different, like 65.72.1.9, you know? So that's a NAT at work. You have lots of private computers and one public device. And this helps with security, and it also helps with using less IP addresses. You don't see NATs as much with IPv6 because there's so many IPv6 addresses it's simply not required, and it adds a level of complexity that you just don't need. So NAT receives a packet like a router would, but what a NAT does is it changes the source and destination IP address as well, because we're masking these IP addresses, and it will change it might change the source port, depending if that port's already in use on that NAT. And then it'll keep track of the connection, because when the data comes back, we need to edit that packet again and send it onto our local network. So here's our NAT walkthrough. We can think of this as our home network, where we have our PC and our NAT router. So our NAT router, say a BT Home Hub, it's a single device, but what it's doing is it's applying some NAT rules, and it's also routing it onto, say, the public internet. So we're going to start again over here. We're going to miss out ARP requests this time, so hopefully you've understood that. Just to say, hey, I want your MAC address, please. That's all an ARP request is. So here we're going to do a UDP DNS request to Google. So you might know the famous Google DNS resolver, 8.8.8.8. So we're going to send a packet there. So our destination is going to be 8.8.8.8. And our source is going to be my local IP. And our layer 4. So we're going to request is 53 is the DNS port, and then we're just going to go with an enemphoral source port. So this is a port that I would like my response on, please. Any port above 1024 can be used for enemphoral ports. Something to bear in mind with AWS is this kind of becomes important when you're looking at firewalls, specifically access control lists, and it varies per operating system what range of enemphoral ports it uses. So let's just say 65123, and then let's do the layer 2 stuff. So the layer 2 is going to say that's my PC there, so that's my source, and I'm going to send it to my router because it's going outside my network. Okay. So this packet's going to come along here, and it's going to hit my router. Now my router needs to change this packet a lot because it's going to send it out onto the public internet, and my source IP address is not routable. These are private IP addresses that if they hit the internet, they will just be dropped. So let's have a look at what we need to change. So let's start from the bottom. Actually, no. Let's start from the top. So layer 4 is our source address. Our source port. 65123. Now, if I have that available on the router, say no one else is actually using it, I might leave that, or I might change it. But I need to keep track of it, whatever the case. So let's keep track of it and say. So first thing to do is to keep track of a record. So we're going to say 192.168.1.5 on port 65123 is communicating with 8.8.8.8 on port 53. Okay, so it's going to keep this record in its NAT table, and then it's going to edit the packet. So what that's going to do is, so let's say it keeps a source port, and then it's going to change this. So it's going to change the layer 3 address, and is going to make that its public IP address. And then it will also change its for layer 2 information, and say the source is now C because I'm going out of this network interface, and the destination, let's say there's a network interface over here that's called D, will be the next hop on its way to Google. Okay, so then that packet is now sent on its way, and when it gets to Google, all of this information will be exactly the same, but your layer 2 information might be different because it's transversed multiple networks, right? So Google's now going to send some data back to us, and that's going to be what it's basically going to do is the source is going to be 53, and the destination is going to be 65123. So it's swapped those around to say, hey, I am 53, and you requested some response on 65123. And it's also going to change the source and destination of these. So that's going to become our destination, and that's going to become our source. So the packet's on its way back, and this might be Google and something, but that doesn't really matter for now because we're looking at our layer 3 and layer 4. When it reaches the when the response reaches the NAT, it's going to say, okay, hi packet, let's have a look in my NAT table to see if this connection is allowed. If it's not allowed, then I'm just going to block you off because you're just trying to break into my network. What are you doing? So the packet's here, and we're going to see this 53 65123. That's our public IP address. Great. So we're going to accept that, and we have this. So let's have a look. We're going to have a look in our NAT table. So our NAT table has this, our 53, and our port. So that's interesting. So what we can do is we can match this up. So we can say that source is 53. Cool, we found a match. Our source IP is that. Cool, we found a match. And our destination port is that. Brilliant. So now we actually know where to send this this packet. So we can change it, right? So we can say that's going to stay the same, but our destination is going to be, we're going to change it back to our private IP address, and we're going to set the MAC level so switching can handle it, and then we're going to send it on its merry way. And that's how the request and the response work for UDP, TCP, any packet, sending it through a NAT and sending it back. And that's where the NAT table comes into play, where it's keeping track of the connections you make, and any connection that, say, hit the NAT public interface and it wasn't stored in the NAT table would just be dropped because it doesn't know where to route for traffic to. So the last part of this video is on firewalls. In AWS you have a stateful firewall and a stateless firewall. The stateful firewall, kind of like a NAT does, keeps track of the connections you have open and allows any returning traffic. And this is where security groups are used, where you define your inbound or outbound rules as allows, and any returning traffic will be allowed basically with that rule. And then you have stateless. Now stateless happens on the lower subnet level with access control lists, and each packet is evaluated independently. So we will allow this packet on port 53, or we can deny all the packets on port 53, for example. We're going to have a look at this in more detail in the next video, because we have security groups and we have access lists, and you kind of have to configure them properly, otherwise you'll get some weird problems For example, if you have a access control list that doesn't allow env reports, like we've just seen in our NAT example, if we block the, if we had an access control list, say, sitting here, and we were to block all our env reports, then it's basically just going to drop the packet and the connection will never be established. So there's those things to kind of keep in mind. We're going to go into detail about that in a later video. So congratulations on making it through that video. I hope you now kind of understand the core networking concepts, and that will really help you when you're looking at a VPC or you're setting up any network, to kind of understand why something happens. It's very easy to kind of get lost in, it just works. But when you understand why, you can kind of troubleshoot in such a way that will just kind of help you resolve problems quicker. For the next video, we're going to have a look at VPC basics or VPC fundamentals. This will look at the core concepts such as subnets, regions, security groups, access lists, internet gateways, NAT gateways, and on VPC. Now we've covered kind of route tables or routers and NATs and IP addresses here, so hopefully you'll now have a firm understanding. So when I go over it in the fundamentals, you can be like, cool, I know how that applies to the whole networking landscape, and then we can crack on and have a tutorial on setting up a VPC, which should be good fun. Hi everyone, thanks for watching. I hope you found the video helpful. If you haven't already, please give the video a thumbs up and hit the subscribe button below for some more great content on AWS, 3D printing and home automation.